Good morning, everyone in pre-calculus land. This is what I hope will be the final one of our live streams for our course this semester, in which we look at some new material. So when we left off on our last live stream, we'd introduced the concept of what it means to be an exponential function and how it is that exponential functions help us to model a new type of behavior and a new relationship between changing quantities in pre-calculus. And so where we want to culminate is we want to take exponential functions and flip them on their heads. What we want to understand is that same relationship that exists between an independent and a dependent quantity that's measured by an exponential relationship. If we turn that relationship around and ask how is the input predicted by the output, we get a new type of function called a logarithmic function. We got a brief introduction to logarithms just from an algebra perspective as a tool for solving exponential equations in our previous live stream. So if you haven't, please do go to that last live stream and catch up to where we are right now on the basic definition of logarithms. Today we want to take that basic definition and really just run with it and ask how can we use logarithms to model behavior that can otherwise be modeled by exponential functions, just reversing the roles of input and output to get the inverse function, as we talked about in our last live stream. And then what are the salient properties that logarithmic functions have, the arithmetic properties of those functions, that are inherited from the corresponding properties of exponential functions. And there's a sort of a laundry list of properties that you can apply to logarithmic expressions and logarithmic equations to try and solve them. And they all come from what I hope are familiar properties of exponents that you learned way back when in your algebra course. It's just that when we're reversing the roles of input and output, we're sort of reversing the roles that the different types of arithmetic played in the properties of exponents that we know and hopefully love so well. So that's the agenda for today. We're going to take a look at a couple of things. First of all, how do we understand logarithms as graphs? So what do graphs of logarithmic functions look like? What are their important properties? And then how do we also understand the ways in which logarithmic functions can give us a new type of function model? So how do logarithmic functions model behavior? And specifically, how do they model behavior in the sense that they relate different types of changes in our input and output quantities to one another? So that's the first big agenda item. And then the second one is that sort of more algebraic item, which is how do we use the properties of logarithms to be able to simplify logarithmic expressions to give us the least amount of cognitive work to do to understand what's happening in a complex expression that has logs as a part of it. So if you're my current student this semester and you're watching this live, welcome. Please contribute your questions via our class Slack channel and I will prioritize those. If you happen to be watching our stream today and you're not a part of my class this semester, you're watching on Twitch, feel free to drop any questions into the Twitch chat as we go along, and I'll try to respond to those as well as we go. So let's get started. So first thing we want to do is try to understand what the graph of a logarithmic function would look like. What are the important properties that the graph of a log function, what properties would we expect it to have? And so for this, I really want to go back to the original definition of logarithms that we had in our previous live stream. And we're going to start from there as our motivation. So what I want to do actually is I want to start with this example. In this example, we're asked to sketch the graph of this logarithmic function. F of x equals 3 times the log of x minus 2 plus 1. The first point that I want to make about this particular example so I want to just focus in real quickly on the form of the expression, the logarithmic expression that we've been given here. 3 times the log of x minus 2. Notice that this logarithm, there's no base written underneath it to tell me what the base of that logarithmic expression is supposed to be. And it's a common convention that when we use the word log in an introductory mathematics course like pre-calculus and we don't specify what the base is, log written by itself typically means log with a base of 10. So 10 is the inferred base of our exponential expression here. So with that caveat, I'm just going to include a little base 10 notation here as part of our logarithmic expression, just to make sure that we're on the same page with that. So the goal here is going to be to try and sketch a graph of this function. But I don't want to do that directly. I want for us to undergo a quick discovery process and figure out what do we expect the graph of this thing is supposed to look like. And to figure that out, what I want to do is instead of graphing this function, I want to graph its inverse function instead. So this is going to be a neat little experiment, and it's also going to give us some practice with using a little bit of algebra, as well as practice with understanding how the graph of a function is related to the graph of its inverse. So if I replace f of x with y, let me zoom in on that again. I replace f of x with y. Then to find a formula for the inverse function, if this inverse function exists, what am I supposed to do? I'm supposed to reverse the roles of x and y in my equation. So we'll just do that. We'll take the y and trade it out with an x. We'll take that x and trade it out with a y. And I'll get 3 log of y minus 2 plus 1. That's a log with a base of 10, right? And so from that, we now need to figure out how to rewrite this expression. And when I rewrite this expression, what I'm expecting is going to happen is that my logarithmic function will turn into a type of function that can best be explained by the inverse of a logarithmic function. And because logs are inverse to exponential functions, we expect that when we rewrite this expression, the result is going to be an exponential function once again. So what is the nature of that reversal going to look like? What do we expect is going to happen? Well, remember from our last video that every exponential expression, some base raised to some power is equal to some quantity, right? B to the x is equal to y. Every one of those expressions has an equivalent form as a logarithmic expression. Log base b of y is equal to x. And so if we want to convert an exponential equation into a logarithmic equation, we can do that. But then what's good for the goose is also good for the gander. We can also go backwards. If I have a logarithmic expression or equation, I can turn it back around into an exponential one instead. So that's going to be our goal here, is to try and understand this as a logarithmic equation. So I want to get this log expression by itself on one side of my equation. And that we know how to do just using the basic principles of solving an equation in algebra. I'm going to subtract 1 from both sides. And subtracting 1 from both sides is going to give me x minus 1 is equal to 3 times the base 10 log of y minus 2. Then I want to divide both sides by 3 to move this 3 out of this logarithmic expression. If I divide by 3 on both sides, I'm going to get x minus 1 over 3 is equal to the base 10 log of y minus 2. And now I'm at a place where I've got that logarithm sitting by itself. So that logarithm has been isolated. That means we're in a good position to be able to rearrange it. So first of all, what's playing the role of my base in this exponential expression? The role of the base is being played by the number 10. It's the base that's sitting here underneath my logarithm. So that's the first thing that I notice here, is that the base in my expression appears to be a 10. What's playing the role of the exponent? What's playing the role of the exponent is it's this x minus 1 over 3. Okay, so rather than just have an x here as my exponent, now I have a more complicated expression. I've got x minus 1 all over 3. And so I'm just making a few adjustments over here. And then the role of y is being played here by a y minus 2. So in place of my y, I'm going to write the expression y minus 2. Okay, so we now need to figure out how to perform the sleight of hand that we need to perform in order to turn this logarithmic equation into an exponential equation instead. So this is going to look a little bit cluttered, but I think you're going to get the point, right? Here I've got the logarithmic equation, log base 10 of y minus 2 is equal to x minus 1 over 3. And so if I want to turn this into an exponential equation instead, the base of my exponential is going to be 10, because it's the same as the base of my logarithm. That's how we define what the base of a logarithm is supposed to be. But the exponent on that 10 is going to be x minus 1 over 3, and the other side of the equation, the power, is going to equal y minus 2. So all we need to do is just do that little do-si-do, and we've rearranged the expression that we needed to rearrange. Take a look at that one more time. Log base 10 of y minus 2 is equal to x minus 1 over 3 means that when I raise 10 to the power given by the value of my logarithm, then the result is supposed to be the argument of my logarithm. 10 raised to the power x minus 1 over 3 is supposed to give me y minus 2. So that's the rearrangement that we need to make. And how we often write that, if we're writing this step in algebra, is we write it as, let's raise both sides of this equation, let's make both sides of this equation the exponent in an expression whose base is equal to 10. So this is often how we write that step that we did here with the animation, right? Converting this logarithmic equation into an exponential equation. We accomplish that just by using both sides of my equation as the exponent in an exponential expression whose base is 10. And then what we can conclude from this is that 10 raised to the base 10 log of y minus 2, that gives me the exponential and logarithm being inverse functions. They cancel one another out. And that 10 raised to the base 10 log of y minus 2 just becomes y minus 2. Right? So that is what we predicted here, just based again on the definition of logarithm. Base 10 log of y minus 2 is x minus 1 over 3 means that 10 raised to the x minus 1 over 3 is y minus 2. And so to finish getting the formula for my inverse function, I just need to add 2 to both sides. And I find out that my inverse function in this example is going to have this equation. Y equals 10 to the power x minus 1 over 3 added to 2. There we go. So what I want to do is I want to graph this function. And then we'll use the graph of that function to determine the graph for its inverse function, which is going to be the graph of our logarithm. And then from that observation, we'll pull out the salient features that will help us to understand how to graph a log function in more generality, so we don't have to go through this algebraic process every time. So let's graph that equation. Y equals 10 raised to the power x minus 1 over 3. And then I add 2 to this. So when I graph that equation, let me make this a little bit darker line here so that we can see it. So when I graph that equation, let's pull out a couple of important features of this graph. So this is my exponential graph that we're looking at right now. It's an exponential function. One feature that I notice right away that sticks out to me is that there is a horizontal asymptote for this graph. And it looks to me like the horizontal asymptote of this graph is situated at y equals 2. It's this horizontal line sitting right there. Make that a dashed line right there. So there's the horizontal asymptote for this exponential graph. And the other thing that I might notice about this is that the value, or maybe I'll say it this way, this function, the y value of this function, f of x, is 1 unit above its horizontal asymptote when x is equal to 1 and when y is equal to 3. So the point 1 comma 3 is a point that I'm kind of trying to zero in on here, right? This is a key, sometimes what we call a control point for an exponential function, is when is it exactly 1 unit above its horizontal asymptote. So that happens at the point 1 comma 3. Let me choose to, I want to label that point here real quickly here. I'll show its value, 1 comma 3. There we go. So that's when my function is 1 unit above its horizontal asymptote. Okay. And so if I want to understand the graph of the inverse function, remember how we get the graph of an inverse function. The graph of an inverse function is obtained by reflecting the graph of the original function across the diagonal line y equals x. So here's that diagonal line, y equals x. And I just want to reflect this graph diagonally across that diagonal line. That's going to give me the graph of the function that we really cared about in this problem, the original. So let's put that graph in its place. And to do that, I'm just going to reverse the roles of x and y in this equation. This is the great thing about having a grapher like GeoGebra. So x equals, you can do this in Desmos also, 10 to the power y minus 1 over 3 plus 2. And when I draw that graph, sure enough, I'm getting the graph that we had here reflected across the line y equals x. And that then is supposed to be the graph of the function that we really cared about in this problem. That function that had the formula f of x. Just make sure to get this on the graph here. F of x equals 3 times the base 10 log of x, what was it, x minus 2, and then plus 1. So that was the equation of the graph that we were really trying to get in this problem. Let me pull it over here so that it's labeling the graph that we really care about. Cool. So there is the graph that we wanted in this problem. And so my question is, what are the important features that we see about this graph? Well, this graph appears not to have a horizontal asymptote, but that makes sense because if this graph had a horizontal asymptote, if the green one had a horizontal asymptote, it would mean that the red graph would have a vertical asymptote, because when you pass from a function to its inverse, everything that used to be x's is now y's, and everything that used to be y's is now x's. We're through the looking glass. All right. And so that means on a graph that everything that used to be horizontal for its inverse function becomes vertical. And because that relationship is reciprocal, everything that used to be vertical for its inverse function becomes horizontal. And so because my original function had a horizontal asymptote, it was an exponential function, exponential functions have horizontal asymptotes, that means that the inverse function will have a vertical asymptote. And so we'll say that this function has a vertical asymptote. I'm typing behind my head here on the video. And the vertical asymptotes equation is going to be the same as the original horizontal asymptotes equation, just with y's replaced with x's. So where my original function had a horizontal asymptote, the new function, the inverse, has a vertical asymptote. And the equation for the vertical asymptote is not y equals 2, but x equals 2. And there it is. Similarly, there's an important control point on this graph, whereas the original function had a control point at 1, 3, where it was 1 unit of distance away from its horizontal asymptote. If we reverse the roles of x and y and label the point 3, 1 instead of 1, 3, that gives me a point on my new graph, where my new graph is exactly 1 unit away from its vertical asymptote. So there is the graph of the exponential function that we really are, sorry, the logarithmic function that we care about most in this problem. Sorry, my iPad's kind of flaking on me for a brief moment here. I just want to get back to where I was before for a minute. Oh boy. So you can't see what I'm doing, but I'm having to adjust my screen a little bit here for just a minute. Trust me, I need to do this now so they don't have to worry about it later. Uh-oh. Almost ready here. Sorry about this. Suddenly just had my whole streaming environment go haywire on me for a brief minute. Okay, I'm almost back to normal here. Just got to do a little bit more. Okay, I think that's better. Oh no. This is the problem with live technology. There are many. There we go. I think we're back to normal. Okay, so sorry for all that stuff that you couldn't see happen just there. But now I think we have an understanding of how we would graph this logarithmic function. Let's go back to our sketchpad. And I'm going to put in the important features. So the first thing that we notice about the original function, so we're going to treat this as it's a graph transformation problem right now, that the original function, my parent function, y equals the base 10 log of x. There's a couple things that we would notice about that original parent function. It would have a vertical asymptote, but its vertical asymptote would be on the y-axis. It would have the equation x equals 0. So let me keep record of this. Vertical asymptote is going to be at x equals 0. Right? It's on the y-axis. And the control point, the point at which this graph would be exactly 1 unit of distance away from its vertical asymptote, would happen at 10, 1. Okay. So here we would have, let's see, 2, 4, 6, 8, 10, 1. Let me just sort of label that point. So here's my original function, my y equals log base 10 of x, and then it would have a point here at, actually no, not 10, 1. Sorry about that. We're going to call this control point 1, 0. Okay, the x-intercept is going to be right there at 1, 0. So this is what my original graph would look like. So that's what the graph of y equals log base 10 of x looks like. Its vertical asymptote is right there on the x-axis, sorry, on the y-axis, the equation x equals 0. And it has this point at 1, 0 that is its x-intercept. Now, if I want to translate this, if I want to apply graph transformations so as to get the equation of the graph that we're actually looking for in this problem, I have a couple things to do. The first thing that I might do is I might do all my stretching and squishing first. So I would stretch this thing by a factor of 3 in the vertical direction. So I'm going to record a few transformational steps right here. So y equals 3 log base 10 of x. This would still have the same vertical asymptote, and its control point would still be 1, 0, but now it would somehow be 3 times as stretched out in the vertical direction. So I'd just be stretching this graph vertically by a factor of 3. And then after I did that stretch, I would shift. I would shift this up by 1. So 3 log base 10 of x plus 1. This would move my graph up 1 unit, and it would move that control point from 1, 0 to 1, 1. 1, 1 is going to be directly above this. So if I shift this graph up, it's now going to be just 1 unit above where it used to be. And now the new control point is here at 1, 1. And then the last step that I would do is replace x by x minus 2. Notice that shifting this graph up is not going to change its vertical asymptote, but replacing x by x minus 2 would shift this graph to the right by 2 units. 3 log base 10 of x minus 2 plus 1. Okay. And when I shift this graph to the right by 2 units, the vertical asymptote that used to be on the y-axis is now going to move over. It's going to move from x equals 0 to x equals 2. And that's what we predicted when we built this graph out of graphing its inverse function. Right, there's my new vertical asymptote, x equals 2. And my new control point is going to move from 1, 1 to 3, 1 instead. So 1, 2, 3, 1. 3, 1 is going to be my new control point. And so my graph ends up looking like that. And that is what we saw on our grapher, right? That was this graph, right? Its vertical asymptote rather was at x equals 2, and 3, 1 right here was this control point. So there is an example of how to sketch a graph of a logarithmic function. We did it in kind of the longer roundabout way by first understanding what is its inverse function, and then we also looked at it from the point of view of graph transformations. Let's do a couple more examples of these graphs before we move off of this topic. So in this example, we want to sketch a graph of f of x equals 1/2 log base 4 of x alongside its parent function. So for its parent function, we're going to use y equals log base 4 of x. And y equals log base 4 of x has a vertical asymptote on the y-axis, like every logarithmic parent function does, and its control point is going to be at, well, let's use 2 control points, 1, 0, and then 4, 1. Okay, so those are 2 points that we know that my original parent function graph is going to go through, 1, 0, and 4, 1. And its vertical asymptote is on the y-axis. So there is my parent function. This is log 4. Y equals log base 4 of x. Okay, so what do I have to do to turn my parent function into this function? This example, there's only one step to do, and that step is we're multiplying this function by 1/2 on the outside. So our new function is 1/2 times log base 4 of x. And so we'll recall from earlier in the semester what happens when I multiply a function on the outside by 1/2. I have done a vertical squish by a factor of 2. So my new graph is going to be half as tall as the old graph was. So that vertical squish, any vertical thing that happens, is not going to change where my vertical asymptote is located. but it is going to move both of my control points twice as close to the x-axis as they used to be. Well, 1, 0 was already on the x-axis, so it doesn't move. But 4, 1 is going to move to 4, 1/2. And so my new graph is going to pass through the point 1, 0, but also through the point 4, 1/2. And its vertical asymptote remains the same. And so what we get is a graph that looks something like this, right? We've squished it by a factor of 2 in the vertical direction down towards the x-axis. Finally, one last example. Here, let's graph f of x equals minus the log of minus x. And again, because this log doesn't specify a base, we're going to infer a base of 10. Anytime they use the word log in precalculus, we're going to infer the base of 10. So if I want to graph this, we're going to start once again from my parent function. My parent function is y equals log base 10 of x. Its vertical asymptote is on the y-axis once again, x equals 0. And its control points we can take to be 1, 0 and 10, 1. After all, the log base 10 of 10 is that exponent which completes the sentence 10 raised to what power is equal to 10. But how do I get 10 to equal 10 when I raise it to an exponent? I need an exponent of 1. 10 to the power 1 is equal to 10. Actually, I should do it this way. 10 to the power 1 is equal to 10. Right. So those are my points. There's my parent function. Let me label those here. There's 1, 0. And then here's 10, 1. I'm not going to take my grid too seriously here. And then my vertical asymptote is on the y-axis. And so my parent function's graph is going to look like this, roughly speaking. So there's my parent function. Now, how do I turn my parent function into this function? Well, we have two things to do. We have to replace x by minus x. So we'll do that in our first step right here. So if I replace x by minus x, then I'll be looking at the graph of y equals log base 10 of minus x. And then my second step is I'm going to put a minus out in front of the expression that defines my function, minus log base 10 of minus x. So these are the two steps that we're going to go through to get from our parent function to the function that we really want to graph. And each of these steps is a transformation that we understand. In the first case, when I replace x by minus x, what I get is a reflection. I get a horizontal reflection. It's horizontal because we're affecting the x variable. It's a horizontal reflection. And when I say horizontal reflection, I mean the reflection over a vertical axis. We're reflecting this graph over the y-axis. Now the y-axis is also its vertical asymptote. So this new function is still going to have its vertical asymptote on the y-axis. But my control points are going to have their x values switch from 1, 0 to minus 1, 0, and from 10, 1 to minus 10, 1. Let me move that to minus 10, 1 right here, because I'm going to have to draw right there in just a second. Minus 10, 1. And so my new graph is going to have this point and this point as its control points, minus 1, 0 and minus 10, 1. And so its graph is going to look something like this instead. There we go. So after one step, I've reflected my graph across the vertical axis here in a horizontal way. And then my second step, when I put a minus sign on in front of my whole expression, that's the same as switching the sign on y. It's the same as replacing y by minus y. And so what I get there is I get a vertical reflection. And my vertical asymptote, when I reflect in a vertical way, remains x equals 0. But now the y-coordinates of my control points are going to flip, which doesn't change my negative 1, 0, but it does change negative 10, 1 to negative 10, negative 1. When I plot those points, here's my negative 1, 0, but my negative 10, negative 1 is now going to be over here. Right? It's going to be on the other side of the x-axis from where we were. And my graph is going to look like this. And so this green curve is the graph of f of x equals minus the base 10 log of minus x. So that's how logarithms work from the point of view of graphs. We can understand really any logarithmic graph just by either converting into its inverse function and then graphing its inverse function as an exponential, or, and this is the more efficient way to do it, just go ahead and graph it using the graph transformations that we already know and hopefully love from earlier in the semester. So, now that we understand how logarithmic functions work from the graph perspective, let's take a step back and ask, what can logarithmic functions do for us from a function modeling perspective? Because we understand how exponential functions model changes in behavior, we also can understand how logarithmic functions model those changes in behavior. And so for that, there's some really good news, right? After all, the only difference between exponential and logarithmic functions is that we're reversing the role of input versus output. Where an exponential function might turn an x into a y, a logarithmic function is expressing the same relationship, but in which y is the input and x is the output, right? So same relationship, just running in different directions, right? So once we understood what the graphs of exponential functions look like, if we interchange the roles of x and y, that's the same as flipping that graph over the x-axis. And when I flip that graph over the x-axis, it turns into a logarithmic shape graph instead, right? So that's how we knew what the shapes of these graphs were supposed to look like in the first place. But when we take an even further step back, we can remind ourselves of how exponential and logarithmic functions model changes in behavior. So for exponential functions, we decided that the way that they work is that they relate additions, so changes in the x variable that we can model with additions and subtractions. It related those additive changes in x's with multiplicative changes in y. So for example, in this exponential function, every time x increases by 1, y increases by a factor of 2. So x goes up by 1, y doubles. X goes up by 1 again, y doubles again, and then doubles again after x goes up by 1, doubles again, doubles again, doubles again, and so forth. So what you're seeing happening in the y direction is that the amounts of change are accelerating. They're getting bigger as we go along, and that's why this graph curves upwards. In calculus, you're going to call a graph like that a concave up graph. So every additive change in x correlates to a multiplicative change in y. For example, if this x variable represents time in years and the y variable represents the amount of available cloud storage in your Gmail account or something like that, right? Then this exponential behavior could be modeled by the verbal sentence that for every year that passes, in other words, every time 1 is added to my x variable, the amount of available cloud storage doubles. So every year that passes means plus 1 in the x direction. Every time the cloud storage doubles means multiply by 2 in the y direction. That's how exponential models work. And so if the goal of a logarithmic model is nothing more than to interchange the roles of x and y, then everything which is true about the x's for exponential functions is now true of the y's for logarithmic functions and vice versa. So a logarithmic model will relate multiplication in the x direction with additive changes in the y direction. So here, every time I multiply x by a certain number, there's going to be a resulting additive or amount change in the y direction that is predictable. So again, this same relationship, which we sort of talked about a minute ago, which if we model this as, I don't know, years and amount of cloud storage, every time the number of years goes up by 1, the amount of cloud storage gets multiplied by a factor of 2. That same relationship is expressed in logarithmic form by saying every time the amount of available cloud storage is multiplied by 2, every time I multiply my x by 2, I'm going to be adding 1 to my y. Right? It's the very same relationship that we're describing in the exponential case right over here. It's just that we've reversed the roles of x and y, and we've flipped the graph across the line y equals x. So not hopefully too many surprises happening here. As soon as you understand how exponential functions model changing behavior, logarithmic functions model changing behavior in exactly the same way, the only difference being the roles of input and output are turned around. Let's do a couple of examples. And I want to draw one example from the world of biology. So we'll look at an example of radiocarbon dating. This is really sort of biochemistry sometimes. And the second example I want to do is a more compound interest, dollars and cents kind of example. So our pre-calculus class that I'm teaching right now has got majors in business, it's got majors in biology, so I'm hoping these examples will have a little bit of something for everybody, regardless of where you're coming from. So the first thing I want to do is I want to just give you a quick introduction to radiocarbon dating for our first example. And in this example, so here's the example. The question is that if we measure the amount of the 14 isotope of carbon in a sample of an ancient piece of pottery, then we should be able to use that measurement to determine how old that piece of pottery was. So when was it manufactured? And so the information given us in the problem here is that the amount of carbon-14 has decreased by 95% since the original manufacture date of this piece of pottery. And we know that carbon-14 gets cut in half every 5,730 years. And we want to know how many years ago was this piece manufactured. So how does radiocarbon dating work? For the scientific explanation, I'm going to borrow from this video, this Scientific American video. It only takes 2 minutes, but I think it's well worth our time. It's going to help us understand why this is really a process that we can model with exponential or logarithmic functions. So let's take 2 minutes and we'll watch this piece from Scientific American called How Does Radiocarbon Dating Work?
How do we know how old something is? For people, we'd ask to see their birth certificate. For trees, we'd count the rings. But how do we know how old a fossil is? Fossils have their own internal clock. Scientists can read it by looking at the ratio of 2 different types of carbon atoms. Of course, every living thing is made of carbon. Plants grab carbon dioxide from the atmosphere and use it to form complex organic molecules. Animals get their carbon by eating these plants. But there's more than one form of carbon. Most carbon atoms have 6 protons and 6 neutrons. We call this carbon-12. High up in the atmosphere, sometimes cosmic rays hit nitrogen atoms. This creates carbon with 6 protons and 8 neutrons. We call this carbon-14. Carbon-12 and carbon-14 behave alike, but carbon-14 has one unique and important attribute. It's unstable. So once an animal dies, the carbon-14 in its body will start to go away. Every 5,730 years on average, about half of the carbon-14 atoms will decay into nitrogen. This is its half-life. After one half-life, the animal will have about half the amount of carbon-14 it started with. After another half-life, it will have about a quarter. And after another half-life, it will have about an eighth. By contrast, the amount of carbon-12 it has in its body will stay the same. By measuring the ratio of carbon-14 to carbon-12, we can measure how many thousands of years have passed since the animal died. Carbon dating works for fossils up to about 60,000 years old. For older fossils, scientists use unstable elements that have much longer half-lives. For Scientific American's Instant Egghead, I'm Michael Moyer.
So thank you to Scientific American for that great explanation of how radiocarbon dating works and why radiocarbon dating works. I particularly like what they did in this video with the graphs, because after all, that's kind of where we're approaching this problem from a lot of ways. If we understand how this graph works, the graph that we just saw in this video, what we're seeing in this graph is that every time the number of half-lives increases by 1, the amount of carbon-14 present is getting multiplied by 1/2. And so we have an additive change in my x variable, if my x variable is the number of half-lives, and it's correlated to a multiplicative change in the amount of carbon-14, multiplication by 1/2. Right? So addition by 1 half-life in the x direction is correlated with multiplication by 1/2 in the y direction. That's what makes radiocarbon dating really a problem about exponential functions. So let's actually take this very same graph and see if we can answer the question that's being posed here in this problem. So to be completely biologically accurate to this problem, we have to imagine that there was something that went into this piece of pottery that came from a living creature. So maybe they ground up some bones or something like that to help make the clay that went into making this piece of pottery. So that there's something in this pottery that we could measure carbon-14 ratios out of that can help us to do the radiocarbon dating on this piece. So let's think about what the graph on this thing is going to look like. If we say, for example, that my x variable is the number of half-lives, so this is going back to the graph from the Scientific American video, right, which I think is a very good one. I'm going to think of these numbers 1, 2, 3, 4 as being my x values, but each one of those is really a certain number of years, right? 5,730 years for each one of the half-lives that we get. So if x is the number of half-lives and y is the amount of carbon-14, then just like in the graph from the video, we're going to imagine that this amount starts out at 1, or if you like, 100%. So we're just going to make that my y-intercept, 100%. And then over time, there is a decay, radioactive decay of the amount of carbon-14. I'll try and draw this as smoothly as I can here. Right. And so there's this decay over time. And after one half-life, the amount of carbon-14 left is 1/2, or 50%. Right? And after two half-lives, well, we multiplied by 1/2 to get from here to here. Let me put in those annotations just to remind us this is how exponential functions work, right? When I add 1 in my horizontal direction, I'm adding 1 half-life to the age of my specimen. And so, according to my exponential function, what I'm doing is I'm multiplying by 1/2 the amount of carbon-14 in this sample. So, exponential functions are gonna exponential function. And so, when I add 1 again to my number of half-lives, then once again, we're going to multiply by 1/2 the amount of carbon-14 in my specimen. And so the total amount at that point is going to be 50% times 1/2, or half of 50%, that's 25%. 25%. And so forth. Okay, so now we kind of understand how this model is behaving. Let's go to the question that's being asked. If we find that the amount of carbon-14 has decreased by 95% since the manufacture of this piece of pottery, well, if it decreased by 95%, often the hardest part about problems like these is navigating the language. If a quantity decreases by 95%, how much of that quantity is left at the end of that process? Well, decreasing by 95% means that only 5% remains. 5% is left, right? And so if 5% is left, then what we're really asking in this problem is how long does it take for the amount of carbon-14 left to decay down to 5%. And so we'd really be asking on this graph to find what x value correlates to a y value that has fallen all the way to 5%. So that question mark right there is how we're trying to sort of answer this problem at the end of the day. So there's the problem. We just have to figure out how to find an answer to this problem. And to do that, let's come up with a model, a formula that we can use to model the behavior that we're seeing here. We can do this using what we talked about in our last live stream, which is the base-intercept formulation, because our graph is already showing us both of those parameters. For instance, the intercept is the value of y when the value of x is equal to 0. In other words, at the original manufacture date of this pottery, 0 half-lives, the amount of carbon-14 was 100%. And so 100% is what we'll take to be our intercept for this function. So there is my intercept, 100%. And the role that that plays in my equation is that it goes out in front of my base, y equals, and I'll put a percent sign in there just for fun, right, 100%. Right. So there's my intercept. And we also are being directly told here what the base of my expression is. In an exponential relationship, the base is the factor by which y is multiplied every time x is increased by 1. And according to what we see here, that factor is exactly 1/2. So the base of this exponential function is 1/2. So we get 1/2 in here, and then that gets raised to the power x, where x is the number of half-lives. Now you might notice, if you've had a biology class recently, that the formula that we've just come up with is not the same as the formula that you likely see in your biology textbooks. It's because we're trying to reason our way into this rather than use a formula off the shelf. I want us to understand how exponential behavior really works and not just use a formula off the rack. We're going to learn later on in today's live stream how to solve exponential equations off the shelf, if you like. But this is a more meaningful equation for my purposes, right? Because I can directly see off of this that we start out, my intercept, after 0 half-lives, we start out with 100% of however much carbon-14. And that every year that passes, every half-life that passes, we lose half. So we multiply our carbon-14 by 1/2. Right? So it's different than maybe the half-life formulas that you're used to seeing, but this will work just fine for our purposes, and I think it's a more meaningful equation to look at and to understand and take apart. Okay, so we have a question in front of us, which is when y is equal to 5%, what is x? So we'll just replace y with 5%. Right? Our y is known, but our x is unknown. 100% times 1/2 raised to the power x. And so what I really need to do here is to get this x by itself. And so I'm going to divide both sides of my equation by 100%. So 5% divided by 100% is going to be my new left-hand side. 5 divided by 100 is 0.05. And then I'm going to be left with just 1/2 to the power x. And now that I have that 1/2 to the power x, I ought to be able to convert that exponential equation into a logarithmic equation instead. So, just to give us the reminder of how that works and why that works the way that it works, let's do that rearrangement. And I'm actually going to use a nifty little tool. We're going to use more of this in a little while. Use a nifty little tool called Graspable Math. This is a really nice website. I promised I would give them a shout out in today's live stream because we've had a great exchange over Twitter just in the last, just this morning actually, about how nifty this particular product is. So I have this equation, and I want to try to understand how to get this x by itself. So I need to rescue x from outside of this exponent and bring it down to earth. But when I do that, well, one way to do it is to try to move it to the other side of the equation, but that doesn't really help because it just trades out an exponent of x for an exponent of 1/x. That's not really what I want to do. So instead, I want to think about moving this x down to earth, down to the base, instead of in the exponent. Well, that's another way to do it, but that still doesn't quite do it the way that we need. What if, and I promised them I wouldn't try to wing this, but here I am winging it. Well, this doesn't seem to help a whole lot, but this might help if we wanted to take a different approach. Actually, let's sit with this for just a second. We're going to use this tool a lot more later on to talk about the properties of logarithms. But for now, I kind of like this because it reminds me of a property of exponents. Right? I'm raising 1/2, a fraction, to a power x. And the distributive property of exponents over multiplication and division tells me I can apply that 1 to the power x to both the numerator and the denominator of that fraction. So I get 1 to the x over 2 to the x. Now I can take this x and raise 1 to the power x. Well, 1 to the power x is nothing more than just 1. So we know that this is just equal to 1 up here on top. And I have 2 to the x down here in my denominator that I can't really do much else with here. Okay, well, why don't we actually do something with this 2 to the x? Because 1 to the x is equal to 1. I can ignore the fact that there's an x up here altogether. Let's just, can I go up there and edit that? Yeah, there we go. 1 to the x is just equal to 1 for all the values of x. So let's just replace that with a 1 and forget about that x in the exponent. Now, to get this x by itself, the next thing I want to do is take this 2 to the x and just multiply by it on both sides of my equation. And then I'll take this 0.05 and divide on both sides of the equation by it. So what this won me, really, this whole process so far, is it's traded out an expression that had 1/2 as the base, now for an expression that has 2 as the base. And now this is something that we understand what to do with. We know now how to get this x out of the exponent. We can get the x out of the exponent, not by doing that, but by using the rearrangement that we have talked about so frequently, right? Let me go back to the original version of this here. Yeah, here we go. So the same way that we already understand for how to trade between a exponential expression, exponential equation, and a logarithmic equation, all I have to do to get that x by itself is transpose the role of exponent and power and turn my exponential into a logarithm. B to the x equals y is equivalent to the log base b of y is equal to x. And so coming back to this example, what I want to do is move this exponent of x over to this side of the equation, and not like that. Move it over to this side of the equation, and this 1.005 reciprocal, which by the way, if we simplify this, it's just 20, right? 1 divided by 0.05 is 20. And so what I'm going to end up with here when I rearrange this equation is I'm going to end up with oops, trade places, get that to the other side. I'm going to end up with x on this right-hand side, and then on the left-hand side, I'm going to end up with the log base 2 of 20. So this is how our equation is going to look at the end of the day. So I did quite a few steps. Let me walk back through them one more time right here. So I ended up distributing this power of x across the division. We're going to do a lot more of that kind of thing in a little while. But what it gave me was 1 to the x over 2 to the x. And then I had 0.05 over here on the right-hand side. And then essentially what I did is I took the reciprocal of both sides, which turned 0.05 into 20, and it turned 1 over 2 to the x into 1 over 1 over 2 to the x, otherwise known as 2 to the power x. And then, and this was the magic step, right? Then I converted this exponential equation into a logarithmic equation, which showed me that x was equal to the base 2 log of 20. Great. So that, from a mathematician's standpoint, is the answer to this question. But of course, if you're a biologist or a journalist or anyone else really, other than a mathematician, you're going to look at that expression and say, well, what in the world number does that actually give me? And really, the problem with the base 2 logarithm is that if you pull out your typical hand calculator, there is no button on this calculator for a base 2 logarithm. There's only 2 log buttons on a typical calculator, the log, which is a log base 10, and the ln, which is a log base e, that we talked about in our last live stream. So in order to finish this question, I'm going to put this on pause until we know a little bit more about the arithmetic properties of logarithms that we're going to talk about at the end of our video today. So when we talk about the change of base formula, that's when we're going to come back and finish this problem. But all of the interesting algebra for this problem is done. We have an answer. We just don't really know what that answer means yet. So we're going to come back to that one later. Let's do the second problem. This is a problem about compound interest. I'm going to zoom in on this a little bit so we can read what's going on. So say I own a small business, and my strategic plan for my small business is that I want to have $1 million in cash reserves sitting around 10 years from now. So my 10-year plan is I want to be sitting on a nest egg of $1 million. And the way I want to get that $1 million is I want to invest $600,000 today. So I throw $600,000 into an interest-bearing account, and then I want to be able to wait 10 years and have that 600 grand grow into a cool $1 million. So the question is, if I'm shopping around for mutual funds or savings accounts or whatever brokerages, what interest rate, what annual percentage yield do I need to get in order to achieve my goal? So let's take a step back here and figure out why it is that this is describing an exponential or logarithmic process to begin with. And what you can see is that what we're talking about is that there's an investment which grows by a factor of 1 plus r. So I multiply by 1 plus r. Every time the amount of money in my account grows by that factor, where r is my annual percentage yield, that correlates to the passing of 1 year of time. Plus 1, right? And so if I think of the time variable as my x number of years, and I think of my account value as my y equals the value of my account, right? Then what this is doing is it's setting up for me an exponential equation. And in the base intercept formulation, the base would be the amount of money at time 0, so $600,000. Right? There's my, sorry, not my base, that's my intercept. Oops, I'm writing off the bottom of the screen here. Let me nudge that up a little bit. Right? So there's my intercept, $600,000. And my base in an exponential equation is the factor by which my output, my y, gets multiplied by every time my input, x, is increased by 1. And so that means that my base is 1 plus r. And again, if you studied compound interest, this equation that we just wrote down probably doesn't look like the equations that you're accustomed to working with, because I'm much more interested in us understanding the mathematics behind this rather than using the formula off the shelf. And again, we'll get a chance in our last phase of our live stream today to use some formulas off the shelf and figure out how they work with just the algebra. But for now, I want to put the focus on the understanding, and this is how it works. We start with $600,000 when x is equal to 0 in my initial investment, and then every 1 year that passes, the amount of money in that account is being multiplied by 1 plus r. And so that forms the base of my exponential equation. So the question now is, what do I know and what am I trying to find out? Well, what I know is I know that I want my amount in my account to be $1 million. And I want that to happen after a total of 10 years have passed. So this is kind of an interesting example because I know a value for y, and I also know a value for x. So my y is $1 million. Right, so that's what came out of this. And I also know a value that I want to use for x. And the value that I want to use for x is that I want that $1 million mark to be reached at the end of 10 years. Right? And so the value of x that I want here is 10. So we just need to figure out how to solve for this value of r. And so this is an interesting example, really, because the unknown quantity for us is no longer in the exponent. Now my unknown quantity, my rate, is sitting down here in the base. And that indicates that because my unknown quantity is in the base, we're not going to need to use a logarithm to solve this problem. My function model was an exponential function model, but because my unknown quantity was in the base and not in the exponent, that means that we can get away with not using a logarithm, which if you're kind of log squeamish, as a lot of algebra students are, this is a great problem for you. Let's just solve this equation for r. How do I do that? Well, I want to divide both sides of this equation by 600,000. So divide by 600,000. And then 1 million divided by 600,000, that's going to be 5/3. If you like, it's 1.666666 ... but I don't like decimals very much, particularly repeating decimals, because we can never actually say all of their digits, and I don't like rounding off. Anyway, so there I divided both sides, and I've got 5/3 is equal to 1 plus r to the power 10. And so now you sort of take another step back, and you say, well, what's going to happen if I want to get that 10 by itself? I've got 5/3 is equal to 1 plus r to the power 10. I want to actually go back to our graspable math illustration for this, just because it's so nifty. So 5/3 equals 1 plus r to the 10th. What should I do in order to try and get this r by itself? Well, the next thing we need to unravel is we need to unravel this 10 in the exponent. And how I do that, if I want to get that 10 out of my exponent, is I just want to kind of drop it over here. And to get rid of an exponent, which is a constant, what we want to do is we want to raise both sides to the 1/10th power. Or another way to say that is to take the 10th root on both sides. And because that 10 was even, we also introduced this plus or minus sign out here in front of the radical. So again, watch that interchange one more time. That 10th power on the right-hand side of 1 plus r is the same as a 10th root, a plus or minus 10th root on the left side of that equation. Now I can get rid of my parentheses. And finally, to solve for my value of r, to get the r by itself, I'll just subtract this 1 from both sides. And here I have my value for r. Right? -1 plus or minus the 10th root of 5/3. Again, for a mathematician, that is a very satisfying answer. But for somebody who wants a number, and if you are working on a compound interest problem, it's very likely that you want a number at the end of this process. Let's take a look at what that might be. So we had the 10th root of 5/3, and then we wanted to add and subtract that from 1. That's the value of r that we ended up with here. So I'll just compute that 10th root by taking 5/3 on my calculator and raising it to the power of 1/10. 1/10 is also known as 0.1. So when I take 5/3 and I raise it to the power of 0.1, what I get is this nasty looking thing, 1.0524. I'm going to kind of round that off. 1.0524. Whoops, this is -1. Right? And then I'm sort of left here with two different answers. If I take -1 and I subtract 1.0524, I'm going to get something which actually doesn't make any sense. -2.0524. So that doesn't seem to make any sense as an interest rate, right? As an annual percentage yield, that makes no sense at all. So for the mathematics, it's a viable answer, but for the context of this problem, it's nonsense. So we're just going to forget that that answer exists. And it must be the other answer, -1 plus 1.0524, otherwise known as 0.0524. That's the answer that does make sense in my context. In particular, if I change that decimal into a percentage, I can do that by moving this decimal twice to the right. I get 5.24. 5.24%, and that's the annual yield that I need on my investment in order to turn my $600,000 today into $1 million 10 years from now when that interest is compounded. Right? So this began as a exponential function model problem, but because the unknown quantity was in the base of that expression rather than in the exponent of that expression, it turned out we didn't need a logarithm to answer this question, which is always kind of a nice thing. But I want to return to the radiocarbon dating example. Right? In this example, we solved this exponential model where the unknown was up in the exponent, and we found out that if only 5% of my carbon-14 is left, that log base 2 of 20 tells me how many half-lives of carbon-14 have elapsed since that piece was manufactured. But we don't know how to evaluate the base 2 log of 20. We don't know what this number is. And so we're going to need to learn some more properties of logarithms to get us through that. And so that is what we're going to do to finish up our live stream today. We're going to look at how properties of logarithms work, how they are motivated by properties of exponents that we already sort of know and love, and then we'll look at some examples of how we can use those properties to actually solve some equations. So let's get started with the properties of logarithms. In particular, we're going to first start out by looking at a property that relates together products and sums. So let's get that show on the road. Get my window set up here. Right, so we know, just from our previous algebra experience, we know what happens when I take two power expressions, a to the power n times a to the power m, and I try to multiply those two power expressions together. The relationship that we had was that the hierarchy, the layer cake of arithmetic, tells me that whatever I do to exponents is going to be one step lower on the layer cake than what I'm doing to their corresponding powers. So if what I'm doing to powers is multiplication, what I'm doing to their exponents is the step below multiplication, which is addition on my arithmetic layer cake. Multiplication of powers, when the base is the same as the addition of their exponents. So remember, logarithms just take everything that we know about exponentials and it just reverses the roles of input and output. So whatever I am doing with the powers, it's happening one step lower to the exponents. Well, that means that whatever is happening to the logarithms is happening one step higher on the arithmetic layer cake to the thing that's inside of the logarithm, the argument of the log. So if inside of my log I am multiplying, then that means on the outside of my log, that multiplication turns into addition. So this multiplication, x times y, if I break it apart, turns into addition, log x plus log y. Again, shout out to Graspable Math website for these great interactive, manipulative pieces we do here, right? So that is the corresponding logarithm property that corresponds to the property of exponents that we already knew, that when I add exponents, it's the same as multiplying the powers of that base. And for that very same reason, when I add logarithms, I get a single logarithm where the argument is the product of those logs. So let's take this to the bank by doing some examples of problems that use the product sum formulation. Right? So here are some examples. I want to start actually with the one that's in the middle here. Let me zoom in on that just so that we make sure that we're seeing this accurately. I want to expand out. This is the base b log of the quantity 8 times k. So I've got 8 times k inside of my argument to my logarithm. I'm taking the log of a product. So that multiplication, I'm going to put a little dot there for multiplication, right, to remind myself that's what's happening in here. The 8 and the k are connected by multiplication. That when I pull that arithmetic out of the log, multiplication inside the log becomes addition on the outside of the log. Right? And so the log of 8k is equal to the log of 8 added to the log of k. And just like the power property of exponents has both of the bases on the left-hand side here are the same, that's also true for the bases of the logarithms. I haven't written in a base here, and so this actually works for logarithms with any base. And so what that means is that the bases of these logs are the same as the base of the original log, log base b of 8, log base b of k. So let me rewrite that just to get it a little bit bigger so that it's legible. Log of 8 times k is the same as the log of 8 added to the log of k. And the bases of those logs are both b. There we go. So there's the first sort of simple example. And if it works for that example, it also works if I apply that logic more than once. So if I have more than one factor that's being multiplied inside of my logarithm, in this example, we actually have 3 different factors. We have 24 times x times the quantity 2x minus 5. So I have really a product of 3 terms, 3 factors inside of my logarithm here. And each one of the multiplications that connects those can be pulled out and turned into addition instead on the outside. So this multiplication will turn into a plus, and that multiplication will turn into a plus on the outside of my log. And what are my new logs going to be that are added together? It's the log of 24. It's the log of the second factor here, which is x. And it's the log of my final factor, 2x minus 5. And the bases of my logs remain the same, so they remain what they originally were in this problem. In this problem, it was a base 3 log that we started with, and so I'll make all these logs base 3 as well. Now, a quick word of caution before we move on. Take a look at this last term, the log of 2x minus 5. You might ask, what happens, or you should ask, what happens when I add or subtract quantities inside of the argument to a logarithm? Can I simplify that? Because it's very tempting to do, but the answer is no. And the reason that it's no is that multiplication inside of a log turns into addition outside of the log because it's one step lower on the layer cake, right? But if I have addition or subtraction inside my log, that would mean that outside the log, we would go one step lower on the layer cake than addition and subtraction, but there is no operation lower than addition and subtraction on the arithmetic layer cake. So I cannot simplify addition or subtraction that happens inside of the argument of a logarithm. So I cannot do anything with the log of 2x minus 5. This is as simplified as it's going to get. So resist the temptation, and I know that the temptation is very real to try and simplify when there's addition or subtraction happening inside of a logarithm. Don't do it because it is not a valid, there's no operation that it can correspond to that can make that piece work. Okay, let's look at the last example here. And in this last example, I want to use this same property, but I want to use it kind of backwards, right? And what I mean by backwards is when I have logs being added to one another and the bases of those logs are the same, I can use this same property but use it backwards. I can take this log x and log y and I can reunite that x and that y, and move over to this expression on the left. So addition outside the log turns into multiplication inside the log. And we can use that fact to simplify this expression, which has logs of the same base being added together. We can simplify it into a single logarithm. So this addition that's happening on the outside, we can move that addition to the inside of a logarithm, and when I move it to the inside, it becomes multiplication. Right. So here's kind of what that looks like. It turns into a single log with the same base as our original logs, 4. Right? But now what's being multiplied on the inside is 8 times 32. So there we've used this product and sum property. We just use it in the opposite way. We had 2 logs added together. We can collect them together into a single log of the product of the arguments of the original logs. Let's actually keep going on this and see if we can find actually a number answer for this. This is going to be the base 4 log of 8 times 32. 8 times 32 is 256. And then the question is, what is the base 4 log of 256? And for that, we'll just go back to our understanding of what is the relationship between an exponential expression and its equivalent logarithmic expression. So this is the thing I've been harping on for the last couple of live streams now. If I want to know what the base 4 log of 256 is, then what I want to do is rearrange that exponential equation, into its equivalent exponential form. So translate between exponential and logarithmic versions of a relationship. So let me get that animation set up for us here real quickly. No, wait, so our unknown, let me just make that a question mark. And the base of my exponential, the argument of my exponential expression. Actually, it's this. Sorry, you're kind of having to adjust some things behind the scenes here. I seem to do a lot of that. Okay, so this is going to look a little bit clumsy, but it'll be better in a second, I promise. Right. So we have the base 4 log. Let me move the word log over a little bit. We have the base 4 log of 256. And I want to know how to translate that into an exponential instead of a logarithmic equation. So we'll just reverse the roles of the 256 and the question mark and find out that the equation we're really asking is what power of 4 gives me 256. Right? If the question mark is the base 4 log of 256, that means that 4 raised to that power is equal to 256. And so this happens to be one that I can just kind of guess and check if I want to. We're going to talk a little bit later about how to solve it in a more systematic way. But the equivalent exponential form gives me a place to start guessing and looking. And it turns out that the power that solves this equation is 4. 4 to the 4th power, you can check, is equal to 256. And so at the end of this problem, it turns out that the answer is equal to 4. If I add the base 4 log of 8 to the base 4 log of 32, what I get in the end is actually just the number 4. So that is that's the product and sum story. So that's how we can use the product and sum properties of logarithms to simplify expressions. But what's good for the product is also good for a quotient. And so we can use this very same reasoning to figure out what we can do if inside of my logarithm I have division instead of multiplication. After all, division is nothing more than the inverse, the opposite operation to multiplication. And so if I know what to do with multiplication, I should also be able to figure out what's possible to do with division as well, just by using another inverse of that operation. So let's look at how this works for the quotients of powers and the differences of exponents. So we already knew back from your algebra class that when I have 2 exponential expressions with the same base that are being divided, that when I divide, that's the same thing as subtracting the exponents, right? Dividing powers of the same base is the same as using that base and subtracting the exponents. And for that very same reason, when I divide inside of a logarithm, the result outside of the logarithm is subtraction. And so there we have the equivalent property for the quotient inside of a logarithm, is that when I take the log of a quotient, I get the same thing as the difference of the logs. So let's use that example. Let's do one or two sort of, maybe just one quick simple example, and then we'll move forward and do some that are a little bit more interesting, let's say. So the example I want to start with here is actually another condensation example. Here I have some additions and subtractions of these various logs happening, and I want to try to condense those to get a single logarithm at the end of the day. Well, we know what to do with addition on the outside of logs, right? That was the first property that we talked about. Addition on the outside becomes multiplication on the inside. And so what I might do here is I might start by turning that addition into multiplication and getting my single log here of the product, 4 times 5. And 4 times 5 being 20, what I've now done is I've kind of gotten this to be, well, and it looks like I've just violated the order of operations. So sorry about that. I'm jumping the gun. What we have here is a bunch of addition and subtraction happening kind of from left to right. And so if I add these two together first, then I'm sort of implicitly putting parentheses around the second and third term, which we really shouldn't do. So instead, what I'm going to do is I'm going to take and I'm going to move this log of 5 and trade places with this minus log of 4. So I'm just going to rearrange that expression. So we'll put the plus log 5 first. So plus log 5. And then after that plus log 5, we'll get minus log 4. Sorry, I'm supposed to set a good example for people as far as the order of operations goes, and I screwed that up. So let me just rearrange the terms to avoid that temptation. And now we can see that what I really ought to do to get this process started is turn this addition outside of my logs into a multiplication inside instead. And so I'll get a single log, and that log is taken of the product, 3 times 5. And then I'm also going to take these, this third and fourth term here, and I'm going to factor out the minus sign from both of them. When I do that, this becomes log 4 plus log 6 on the inside. And that lets me once again use the product to sum property that we know to turn this into multiplication. Multiplication of 4 times 6 inside of my log. And I still have that minus. And so what I'm going to end up with here is the log of 15 minus the log of 24. Okay. And now we're in a position to take the subtraction that's happening outside of the log and turn subtraction outside of the log into division on the inside of the log, according to the quotient to difference property. And so subtraction on the outside becomes division on the inside. I'm going to use this old-timey division sign that gets Facebook into a whole lot of trouble. And we'll get log of 15 divided by 24. And there it is. And if we want to, we can simplify 15 over 24, because that has a common factor of 3. That's the log of 5/8. And that's as far as we really need to go with this. I mean, if we really want to know what a decimal for that is, since this log appears to be a base 10 log that we've started out with here, I can just do 5 divided by 8 to get a decimal for 5/8 on the calculator, and then I'll just hit my log button. And I get something like negative 0.2-ish or so as the answer to this. But the most important thing is, how did we use the properties of logs to condense this sum and difference of logs that have the same base into a single logarithmic expression? All right, let's move forward and do a couple of more examples that are using both the product and the sum properties at the same time. I want to look at this somewhat nasty looking example that we started with up here. All right, so I'm going to use Graspable Math's interface here to do this example. So I want to expand this out so that instead of all of my arithmetic happening inside of the log, I want all my arithmetic to be happening outside of the log. So what can I do? The first thing that I see when I look at this expression is I see a bunch of division. I see an expression divided by another expression. So the first thing I want to do is to try to get this division on the inside outside of my log. And according to our properties, right, outside of a log becomes subtraction when inside of the log it's division. So what we'd expect is that if I take any one of these factors from the denominator outside, it's going to be subtracted. So I take the x minus 1 outside, and it becomes minus the log of x minus 1. I take the x minus 2. Whoops. I grab the x minus 2 and take it outside. It becomes minus the log of x minus 2. I'm going off the screen a little bit here. I take that 7x outside. Well, I take the 7 outside, if you like. It becomes minus the log of 7. I take this x to the outside. It becomes minus the log of x. So all that stuff that was in the denominator, when I bring it outside, it becomes minus the log of that factor. Okay, what about the numerator, 7x squared plus 21x? Well, we can do some factoring on that expression a little bit, because maybe at the end of the day we'll be able to make this a little bit nicer. I factor out that 7. Looks like I might need to zoom out a little bit here or something. How could I do that? This work? Yeah, there we go. So I pull that 7 out, and then take a look at what I can do. Because this is 7 times x squared plus 3x, I can pull my 7 out. It's multiplication inside. On the outside, it becomes addition, plus log 3 of 7. But I've got this log 3 of 7 both added and also subtracted here. So those end up just canceling one another out. So that's kind of nifty. I can do the same kind of trick over here with my x squared plus 3x. If I factor out an x from that expression, x times x plus 3, now I can rescue this x times x plus 3, that multiplication inside becomes addition on the outside, plus log 3 of x. And once again, I've got a plus log 3 of x and a minus log 3 of x that cancel one another out. And now I'm finished. Now I've done all of my simplifying using the properties of logs. Let's rewind the tape a little bit here and just see what it was in total that we ended up doing. So we started with this somewhat complicated expression that's got a lot of multiplication and division going on inside of the log. All of the division that was happening inside of the log, those factors in the denominator, we pull those out of the log and they become subtraction. So we were subtracting the log of x minus 1 and the log of x minus 2 and the log of 7 and the log of x. Okay, so all those got subtracted because they were being divided by on the inside. Now everything that's left on the inside is just multiplication and addition. When I factor the expression that's on the inside, I can factor out a 7. And when that 7 is factored out, it becomes 7 times that thing, and that multiplication inside becomes addition on the outside. But now I've got a log of 7 and a minus log of 7 that end up just annihilating. Right? They cancel out. Similarly, when I factor an x out from that expression on the inside of the log, x times x plus 3, that multiplication becomes addition on the outside by log x. But now that log x and this minus log x cancel one another as well. And this expression is as simplified as it can possibly be. And the reason I know I can't do any more simplifying is that inside of my logs, I no longer have I no longer have multiplication, and I no longer have addition. I no longer have division. I only have addition and subtraction. And addition and subtraction inside the log is the one thing that we cannot simplify any further. So this then becomes my final answer to this problem. So it's the log of x plus 3 minus the log of x minus 1 minus the log of x minus 2. All those logs have the same base as we started with. Right? Sorry, I just ran off the screen a little bit there. So there's what we get after a number of algebraic steps. All right, so if that's the story for quotients and differences, let's go that one more step up the arithmetic layer cake to our highest layer on the cake. And that highest layer is exponentiation. So we have an exponent rule that tells us how to simplify when I have a power of a power. And the question that we want to ask ourselves now is, what happens in a logarithm? What is the corresponding property of logarithms that should happen that correlates to this power of a power property? So above my head right here, we know how to simplify a power of a power. when I take a power of a power, those exponents multiply. Right? That's one of the fundamental properties of exponents that we learn. So what then should happen if an exponential takes exponentiation of a power and turns it into multiplication of exponents? We reverse that role for logarithms. So when a logarithm has an exponent happening on the inside, on the outside what we should see is multiplication. So the log of a power is a multiple of that log. In other words, the log of x to the power y can be rewritten by taking that y outside the log and making it multiplication. Very often in a textbook you'll see it written out in the front like this. So often how I like to see this is that a power, when the argument of my logarithm inside is being raised to a power, we can just take that power, that exponent, and just pull it out in the front and make it a multiple instead. Right? So there is the equivalent version of the power to product property for exponents becomes a product to power property for logarithms. So let's look at a couple examples where we can use that power property, but to expand and also to collect a logarithmic expression. These ones are going to go by a little bit more quickly because there's a little bit less to do. It shows some rather simple examples for this one. So let's start with the one up here on the top. The log base 5 of x squared. Well, my expression on the inside is the power, the second power of x. And so according to our exponent to multiple property, we're just going to take that second power and make it a multiple of 2 out in the front. So we get 2 times the log base 5 of x. Right? Same thing happens in the second example. Natural log of x to the power 4. Remember, and this is the first time for us talking about this today, natural log is not some mysterious thing. It's just the log whose base is the natural number e. So we don't have to treat ln any differently than we treat a log base 5 or a log base 10 or any of the other logarithms that we study. Okay? And so that very same power to multiple property that holds for any other log will hold for the natural log as well. The log of the fourth power of x is nothing more than the fourth multiple of the log of x. The next example is one that sort of flies under the radar screen a little bit. This is something that by the time students get to calculus, this is the kind of thing that tends to bite people a lot more than anything else. So we see 1 over x squared here. And the strategy that we're going to use in order to figure out how to approach this is we're going to rewrite 1 over x squared, rewrite that exponential expression as a power of x. 1 over x squared, if I move that x squared from the denominator up to the numerator, its exponent changes sign. And so really, the exponent that I have on my x inside of my logarithm is negative 2. So I've really got the natural log of x to the power negative 2. This is a step which, if you remember this step, you're going to pull out a lot less hairs when you get to calculus, because there's a lot in calculus that you need to be able to convert into negative exponents and fractional exponents in order to do. But now that it's in this form, we can apply that same power to multiple property. Minus 2, which is a power inside the logarithm, becomes a multiple outside the logarithm. Negative 2 times ln of x, natural log of x. I actually want to do one more example before we move off of this. Let's suppose that I had the base 10 log of the square root of x squared, or of x cubed, let's say, right? So this is also something that we can use an algebraic strategy to simplify. Before we do anything with properties of logs, we have to do something with the exponents that we have at play here. Let me just section this off from the previous example that we did. After all, what is the square root of x cubed? The square root of x cubed, as we talked about very early in our semester, we can rewrite that as x with a single exponent on top of it. And that exponent is going to be a fraction whose numerator is 3 and whose denominator is the index of my radical, which is 2. The square root of x cubed is nothing more than x to the power 3/2. And so the algebra move that I'm doing here is I'm just rewriting that radical as having a fractional exponent instead of thinking of it as a radical expression. Again, super important thing in calculus. You'll pull out a lot fewer of your hairs next semester if you remember that kind of conversion from radical into fractional exponent. And now that it's a single exponent on the inside, even though it's a fraction, it doesn't matter. We can use the power to product property of logs to make this, instead of the log of the 3/2 power of x, it's the 3/2 multiple of the logarithm of x. And there, that example is done. And the last example that I want to do is just an example of using this property backwards. So instead of using the property to rescue an exponent from inside the log to the outside, I want to use it to take this multiple and bring it back inside instead, right? We can run all of these properties in either direction. And so the example we're looking at here is just to the other side of my head here, 2 times the base 3 log of 4. How do I rewrite that so as to bring that multiple back to the inside? Well, this multiple of 2, I can bring it back to the inside, and I end up getting a single log, base 3, of 4 to the power 2. Bingo. And if we want to simplify that, it's the base 3 log of 16. And again, the base 3 log of 16 is not a number that we know how to compute. If I want a decimal approximation, for example, my calculator does not have a log base 3 button. And so we need one last thing in order to compute the base 3 log of 16, or to compute the base 2 log of 20, which answered our half-life question that we posed in our application problem a little while ago. In order to evaluate those logs, what we need is a way to change the base of those logarithms. I don't know how to take the base 3 log of 16, but my calculator knows how to take the base 10 log of 16. It knows how to take the base e log of 16. And so if I can somehow change this expression to have a different base, then I'll be able to use a calculator to evaluate it. And so this key is called the change of base formula. And it's probably the most practically valuable property that we study of logarithms. And now here's how it works. Bear with me a little bit, because this is the most technical of these properties, but the most practical, useful. The first thing that we observe is that any exponential, a to the power x, okay, I can take that x up in the exponent. I can rewrite it as the base b log of the exponential b to the x, right? After all, this is what logarithm means. The base b log of b to the x is the answer to the question, what power of b is going to give me b to the x? And that answer is always x. So x is the same as the base b log of b to the power x. But that observation also allows me to write the following thing, right? If I'm interested in the base a log of x, then the base a log of x is equal to itself if I multiply on both sides by the base b log of a. I'm going to be able to do something interesting. What I'm going to do here is I'm going to use the power to multiple property of logarithms that says that multiplying logs is the same as having an exponent on the inside of the logs. It's the property that we just talked about. But I'm going to use that property in a clever way. And the clever way that I'm going to use this property is I'm going to take this log b of a that's sitting right here, and I'm going to move it to the inside to make it an exponent on my x. Wait, that's not quite what I wanted. Hold on. Let me back up a step. I actually want to do it the other way around. I want to take this log base a of x, which is sitting on the outside, and I want to move it to be an exponent on this a that's on the inside of my log. Right? See how I just did that? Let me back that up just a step so we can do it one more time. Right? Log a of x times log b of a. I want to take this quantity, log a of x, and instead of multiplying on the outside of this logarithm, I'm going to turn it into an exponent on the inside of that logarithm. But now maybe you can see what happens, why we would want to do that. Because now inside my expression, I have a to the power log a of x. But what is a to the power log a of x? By definition, that's just x. And so, what we find out here at the end is that I'm able to simplify my expression, but now I have two different types of logarithms in my problem. I've got a base b log on both the left and right hand sides, and I also have this base a log on this side. So if I drag this base b log over to the other side, divide both sides by log b of a, then what I have all of a sudden is an equation that has only base a logs on one side. Let me flip-flop the sides here. It has only base a logs on the left side, and it has only base b logs on the right-hand side. And this is the famous change of base formula. This is the big deal. If I could draw a smiley face with my mouse, I would. I mean, we're going to have to call that a smiley face. This is the magic formula, the change of base formula, that is going to let me transform any logarithm with a base that's scary or interesting and transform that logarithm into an expression that is the quotient of the logarithms with any base that I want to. So this b can be absolutely any base that we like, right? It doesn't have to be 10, it doesn't have to be e, but those are the ones that your calculator knows about, right? So that is my change of base formula. Let's go back and use it to, first of all, revisit the question of the log base 3 of 16 that we just set down a moment ago. According to the change of base formula, if I replace the role of a here by 3 and the role of x by 16, then the log 3 of 16, according to the change of base formula, is supposed to be equal to the log of 16 divided by the log of 3. And you'll say, well, what are the bases for these two logs on the right-hand side? And the good news is, it doesn't matter. You get to pick any base that you want. As long as you pick the same base for the numerator as you do for the denominator, it does not matter at all. So I could make this log base 10 of 6 and log base 10 of 3, and that would be fine. This now gives me an equivalent expression, but now I can evaluate this expression using my calculator because it knows how to do base 10 logs. So I'll take the base 10 log of 16. That gives me approximately 1.2. I'll take the base 10 log of 3. That gives me approximately 0.47. I'll divide those two, and at the end of the day, I get this decimal, 2.523. The magic of the change of base formula. There we go. That's the log base 3 of 16. So if you are going to take only one formula, one property, one strategy away from our long discussion of the properties of logs, this change of base formula is probably the one that you're going to use the most because it lets you evaluate logs of any base using any technology that you like that's capable of doing any logarithm at all, right? Because you can choose whatever base you want on the right-hand side. So with that in mind, let's end by revisiting our half-life question. How old was my sample of pottery, given that we measured that 95% of its carbon-14 had disappeared since it was manufactured? When we solved the exponential model, we got this number, log base 2 of 20. That number was supposedly the answer to our question. But we didn't know how to evaluate it back then. Now we do. So let's do that legwork to finish up this example. How do I do the log base 2 of 20? Well, according to the change of base formula, that's going to be equal to the log with any base that I like of 20 divided by the log with that same base of 2. Just for the sake of fun, let's choose a different base this time. What if I choose the base e log, otherwise known as the natural log? If I choose the base e log, then often we'll call log base e by its other name, the name in which you'll find it on a calculator button. Call it ln. So that's the ln of 2 in the denominator, and it's the ln of 20 in the numerator, right? And so then I'll take out my calculator once again. I'll take the natural log of 20. It gives me roughly 3 or so. I'll divide it by the natural log of 2, which is about 0.69, and I get 4.322 or so. So there is what the change of base formula tells me about this answer. I'm going to make a little bit of room for myself here. 4.322. Okay, and so that is my value for x. But in order to answer this question, remember the question asked how many years old was this piece? How many years ago was it manufactured? And in our problem, x corresponds to the number of half-lives, not the number of years. So all we need to do is a quick unit conversion. So if x was 4.322 half-lives, then to get the number of years out of this, what I want to do is multiply that 4.322. Make myself a little bit of room here again. I'm going to multiply that 4.322 by a unit conversion factor that can tell me the relationship between years and half-lives. And that relationship, according to our statement of the problem, right, that every half-life is 5,730 years, then I'll just multiply by that conversion factor that says 1 half-life is the same as 5,730 years. And then my units, half-lives, half-lives, cancel. And my new units that survive are years. 4.322 times 5,730. Pull out my calculator one more time. Do that multiplication. Gives me this number right there, 24,765, if I round that up. And that would then be how many years old this piece of pottery is. 24,765 years. And that would then answer our question. So knowing how to change the base in a logarithmic expression is a big deal because it is how we are able to do any of these logarithms with other bases that we might be interested to do. Okay, I lied a little bit. There's one last topic that I want to tackle in our live stream, and we're going to do this one with some haste because I definitely don't want to go over the 2-hour mark today. And the last topic is this. How do I solve equations using everything that we know about the properties of logarithms? So here I have 6 different examples divided into 3 categories, and they're kind of an increasing order of challenge level. We're going to start with the ones that are the most straightforward, the ones that are going to require the least amount of knowing properties of logs and so forth, and then we're going to work our way up through we're going to work our way up through the examples that are a little bit more interesting and complex and that are going to require us to use a little bit more of our knowledge about the properties of logs. So let's start with the example on top here. If I'm solving an exponential equation where both sides of my equation are exponential expressions with the same base, that's really good news because if the bases are the same, then that must mean that the exponents are the same. And that reason for that is because every exponential function passes the horizontal line test, right? If I plug 2 different values into the 6 to the x function, f of x equals 6 to the x, then I will necessarily get 2 different outputs, because any horizontal line only intersects the graph once. So when my 2 sides are exponential expressions with the same base, it must mean that the exponents must have been the same. And so in this example, we'll just take those 2 exponents and set those exponents equal to one another. And now I have an equation that you could have solved many years ago when you took your first algebra class, right? We can add x to both sides. We can add 8 to both sides. And then we can divide by -8 and get x equals -1. And that's all there is to it. Right. So when the base is the same on both sides, we'll do one more quick example here. When the base is the same on both sides, we have nothing more to do than to just equate the exponents. 2x, 3x plus 2. And we solve that the same way that we always knew how. Subtract 3x from both sides, multiply by -1, and we're done. Okay. So when both sides have the same base, it should be just kind of rolling off a log, right? Just equate the exponents and you're all set. So it's when we have exponential expressions with different bases on both sides that things are a little bit more interesting. But it's not so bad if those bases are related to one another. So in this example, I have an expression whose base is 4 and an expression whose base is 16. Now, what we could do is we could try and transform this problem into a problem like we already know how to solve. That's using your problem-solving brain. And the way we could do that is just by noticing that 16 is related to 4. In fact, 16 is already a power of 4. And so one strategy, this is the one that I prefer whenever we can use it, is just to replace 16 by its equivalent power of 4. And 16 is just 4 to the power 2. And the reason that that's good news is that now on the right-hand side, I have a power of a power, right? 4 to the power 2 to the power x plus 1. And when I have the power of a power, we know what to do with those exponents. We can multiply them. 2 times the quantity x plus 1 becomes my exponent on a single power of 4 on the right-hand side. And now look at what we have. We have an exponential equation with the base on both sides of my equation being the same. And so we can borrow the same strategy that we used before and just equate the exponents. X plus 2 is equal to 2 times the quantity x plus 1. And then we would solve this in the usual fashion. Simplify the right-hand side. I'm going to subtract 2x from both sides, and I'm going to subtract 2 from both sides. I find out x is equal to 0 is my solution to this problem. So that's the way to do it using the strategy that we've already talked about. But what if we can't use that strategy? What if we have an example like the one down here, where I've got a 2 and I've got a 3, but it's not obvious. I mean, it's true, but it's not obvious what power of 2 is going to give me 3, right? It wasn't obvious like 16 is 4 squared or 25 is 5 squared. I'm not going to do this example because it's too similar to this one. So if I had an example like this, which, by the way, I think you can't quite see it, but I'm going to write it in here. There's a minus in front of this x, so that's 3 to the negative x plus 1. In that example, we're going to need something a little bit more high-powered. So we're going to come back to that one in a moment. Before we do, let's look at the first of these last two examples, which is, what about this one? 9 to the power x minus 10 is equal to 11. Well, this is one that we already knew how to solve. All we have to do is transform the exponential equation into a logarithmic equation instead, using everybody's favorite little animation that I keep putting in front of your face over and over again, which is here we go. Hopefully you're sick of this by now. We can just change that exponential into a logarithmic expression or vice versa, right? So just reverse the role of the exponent and the power and turn your exponential into a logarithm with the same base as we started. So in our example, the base was 6, the exponent was x minus 10, and the power was 11. So that 11 is going to end up inside the log, that x minus 10 is going to end up outside the log, and we're going to have a log base 9. So when I turn this into a logarithmic expression, this x minus 10 is going to go over here, that 11 is going to come over here, and that 9 is going to turn into a base 9 log. So here is what we end up with. We get the base 9 logarithm of 11 is equal to x minus 10. And if I'm solving this equation for x, all I then need to do is add 10 to both sides, and I'll find out that x is equal to 10 plus the base 9 log of 11, which is a perfectly satisfying answer for a mathematician, but for somebody who likes numbers and decimals, we would probably want to use the change of base formula to get a decimal approximation for the base 9 log of 11. And remember how that works. The base 9 log of 11 is nothing more than the ratio of the log of 11 to the log of 9. And those logs can be chosen to have any base that we like. Cheat that over there just a little bit. So, I don't know, maybe we'll choose base 10 log. Who knows? And then I have 10 plus out in the front here. I'll pull out my calculator, take the base 10 log of 11. Oops. Base 10 log, whoops. Base 10 log of 11. I'll divide it by the base 10 log of 9. I get about 1.09. I'll add that to 10, and I get about 11.09. Okay. So the key there was just transforming from exponential form back into a logarithmic form in order to solve that problem. So what does that mean about this last and sort of scariest example of how we can use these properties of logarithms to solve this equation, 2 to the x equals 3 to the minus x plus 1? Well, my favorite way of solving a problem like this is to pick one of my two bases, either base 2 or base 3. Let me say I'll pick base 3. I like to pick the one that has the more complicated argument. And I'm just going to apply the base 3 log of both sides. And the reason that that's advantageous is that my right-hand side is already a power of 3. My left side is not, but we're not going to let that stop us. So I take the base 3 log of both sides. I get 2 to the x on the inside of this. I get 3 to the minus x plus 1 over here. Right. But what can I do now with this equation? Well, we have the power to product property of logarithms that tells me when I have a power inside of my log, I can trade that out for a multiple on the outside of my log. So I'm going to take those powers, I'm going to bring them out. What I'm going to get is x times the log base 3 of 2. That's my new left-hand side. My right-hand side is going to be, careful with parentheses, minus x plus 1 times the log base 3 of 3. And the great news now is that all of my x's have been rescued from the exponents, and they're all now down to earth on the base. The other piece of good news is that because I chose a base 3 logarithm to apply here, I'm left with the base 3 log of the number 3, which is the answer to the question, how many powers of 3 does it take to make the value 3? And that answer, as it always is 1. The base 3 log of 3 is just equal to 1. And so that's an invisible piece of arithmetic. We don't even need it. And so now to finish, I just have to add x to both sides, and I'll get x times the quantity log 3 of 2 plus 1. And then I'll just divide by this nasty thing, 1 plus the log base 3 of 2, and that will give me my final value for x. X is 1 over log base 3 of 2 plus 1. And yet again, if we want a decimal approximation for log base 3 of 2, we would have to hit that with the change of base formula, rearing its ugly head once again. I would get the log of 2 divided by the log of 3 for that expression. We can choose whatever base we want to. So I don't know, maybe we'll choose a base of e, make this a natural log again. And then I take the natural log of 2 on my calculator. I divide it by the natural log of 3 on my calculator. I get a number. It's approximately 0.63. So I'll take that 0.63, I'll put it downstairs, I'll add 1 to it, and I'll take the reciprocal, and then I have my final answer, which is approximately 0.613. But the decimal is not the point. Right. The point is all the algebra that took us from the original statement of the problem down to our answer. And to get there, we use several properties of logarithms, the most important of which is that we use the power to multiple property that lets me pull out this exponent from inside of the logarithm and make it a multiple on the outside of the logarithm. And then the only other property that we really needed in order to get our decimal approximation for this answer was the change of base formula, the almighty, all-important change of base formula, because that is then the formula that allowed us, that's the formula that allowed us to, just look back at it one more time, right? I had a base A logarithm that I didn't know the value of, and so I turned it into a ratio of base B logarithms that we can compute, right? In this case, we chose a base of E and made them natural logs, so that the base 3 log of 2 can be evaluated as the natural log of 2 divided by the natural log of 3, and that's what helped me get my decimal approximation for my final answer. Whew. So that's going to close the book on our lesson on the properties of logarithms and modeling with logarithmic functions. That also closes the book on our exposition of new material for this semester of pre-calculus. So if you've made it this far and you're my current student, that's as far as we go. I am going to schedule some time next week because we're going to start working on revisions as well as on our final exam next week. That's going to be the main item of business. So I'm going to schedule a couple of live streams that are going to be focused just on your needs. So the questions that you have, we're going to do some review in live stream format next week. And so no new material after this. If you've been watching the series of live streams, I hope that you found some of them to be helpful. And it's been a lot of fun for me to put these together and do them for you this semester. We did this over the course of a shortened 5-week summer term. So if it felt like we were going fast, pre-calculus is already a fast course, and we had to go even faster because our whole class was 3 times as short. It's like we horizontally compressed the semester by a factor of 3. But hopefully you got something out of it, and I hope you enjoyed watching this as much as I enjoyed making it. And I'll see you elsewhere, both when we come to our review live streams next week, as well as in my future teaching down the line. So I hope you enjoyed. Thanks.